The Watts organization has been ceasing in its efforts to promote safety by demonstrating the seriousness of hot water overheating explosions. As early as 1939, various tests and overheating demonstrations were held, and several hundred representatives of the plumbing industry witnessed hot water tanks actually exploding. Explosion danger lurks in thousands of typical hot water heater installations because the great majority have either improper protection or no protection at all. It's hard to realize that an overheated tank can be dangerous, but 30 gallons of superheated water can explode with violence, causing destruction. Destruction. One person was killed and 10 hurt in this tenement house explosion. It cost nearly $10,000 to rebuild this house after a gas hot water heater exploded. This was a clubhouse, completely demolished by an explosion of an 80-gallon electric water heater. No protection whatever. Now, look at this. The tank went right up through the bathroom and stuck in the ceiling. Many of these tank explosions cost only property damage, but it is lucky more people haven't been fatally hurt. An ordinary heater exploded in this cafe and blew the front right out on the sidewalk. This apartment house suffered heavily from a tank blast. In order to witness the effects of an explosion happening in a home, Watts built model houses and caused an overheated 30-gallon tank inside to rupture. Cameramen record the tremendous force and resulting damage. Watch it go. The tank landed over 500 feet away. A bomb could not do a better job of destruction. Notice the barricade and pit in the foreground which protected the engineers from flying debris and parts of the tank. To carry out further field test demonstrations, tanks are set up in an open field and connected to a water supply. As the tanks are being heated, barricade and pit enable safe observation through this periscope. A thermocouple in the tank is connected to this temperature recorder, which gives accurate readings of the rising water temperature tabulated at frequent intervals for complete engineering data. Later, a water hammer condition was created in the tank which caused the shell to rupture at a predetermined time. When the superheated water reached 300 degrees, here's what happened. And the engineers almost got a steam bath from this explosion. It is obvious that temperature must be controlled to assure safety in hot water tanks. To continue this experiment in the field, a heavy-duty tank is set up and heated by a gas heater. A pressure relief valve on the water supply line is dripping steadily at 75 pounds, taking care of the thermal expansion of the water. But the temperature continues to rise, and when it reaches 302 degrees, cameramen spotted at strategic points are alerted for action. The superheated water is subjected to a hydraulic water hammer. Notice steam escaping from the bottom. Suddenly it ruptures and blows off the bottom head. As the tank explodes, the copper tubing and control lines are ripped up into the air with the tank. These slow motion pictures show the rocket effect of the explosion caused by the superheated water generating steam pressure energy which propelled the tank several hundred feet in the air. There it comes down, and here it is. In spite of the plain pressure relief valve maintaining normal pressure, this tank exploded. To demonstrate the effects of excessively high pressure with low temperature, this hydraulic hand pump is increasing normal pressure in an extra heavy tank. Now the pressure is nearly 300 pounds. Still going strong at 400 pounds. At 500 pounds per square inch, there is over 1 million pounds total pressure pushing against the entire inner surface of this tank. But we're not afraid of it, and step right up to the tank with a pointed hammer and wham! Did you get wet? We did, but no explosion, because no heat energy to release, just pressure. To explain the behavior of water above atmospheric boiling point, this chart shows the comparative boiling points at various pressures. These are standard physical factors. The higher the pressure, the higher the boiling point. Atmospheric pressure at sea level is 0 gauge, at which point water boils at 212 degrees Fahrenheit, as in this open beaker. No matter how much heat is added, the temperature cannot rise above 212 degrees. The water boils and changes to steam, passing off into the atmosphere. But under pressure, more heat is absorbed by water before it boils. For example, at 30 pounds pressure, water will not boil until temperature reaches 274 degrees. At 60 pounds pressure, water boils at 307 degrees. But when a 30-gallon tank explodes, at 297 degrees with 50 pounds pressure, it liberates over 2 million foot-pounds of energy, or more than that released by 2 pounds of dynamite. In this glass tank, we will illustrate another serious hazard of overheated water, which is common to open main systems. When the superheated water starts to boil, steam forms and displaces the water, forcing it back into the cold water supply line. As the volume of steam increases, it overcomes the water main pressure and pushes this boiling water further and further back. Should a cold water outlet be opened, this steaming water can cause personal injury and also toilet closet breakage from sudden high temperature. This is also what causes burned out meters. However, of greater importance, if a tank ruptured due to heat weakening and corrosion, This superheated steam and water, when liberated to atmosphere, would explode with tremendous violence. If all the water is forced out of the tank, something has to give way eventually. Now we install a temperature relief valve in the hot water outlet and record temperature in the top of the tank with this thermometer. When the water temperature in the tank reaches 212 degrees, the fully automatic temperature relief valve begins to operate. Steam and the thermometer on the drain outlet show that hot water is escaping through the relief valve, and the thermometer shows a drop of the water temperature in the tank as cold water replaces the hot water. Therefore, to prevent explosions and overheating hazards, install combination temperature and pressure relief valve so as to discharge the hottest water from the top of a tank. Watts has conducted several explosion demonstrations publicly, which were carried out the same as factory field test demonstrations described earlier in this film. Tanks and equipment were placed in an open field for observers to watch. Startled cameramen managed to catch these after effects when two steel tanks exploded ahead of schedule at unusually low temperatures. When explosions in actual service do occur, they happen just this way. In this small cabin, a 30-gallon copper tank exploded when a water hammer condition was created, causing the shell to rupture and tear off the upper half. Another camera shot of the explosion shows where the upper half went. It was propelled to a height which observers estimated to be 400 feet and landed 450 feet away. Here's the top part of the copper tank. Flashing superheated water caused this, not pressure. To summarize, excessive pressure relief protection alone cannot prevent overheating hazards or lower the water temperature. And only water temperature above atmospheric boiling point has the energy to cause explosions and overheating hazards. Scenes of destruction from hot water explosions, like this one in a basement and this one of a factory, serve to remind that water, when superheated, isn't just water. It's a latent destructive power which, when released to the atmosphere by rupture, is like a bomb, causing damage and destruction to property and injury to people. Therefore, as many cities have done, it is very essential that safety measures be adopted to require proper temperature and pressure relief protection for public safety.